Our next speaker is Aline Zanardini from EPFL, who will be talking about GIT for linear systems of hypersurfaces.
Yes, thank you. So, hello everyone, including those of you joining us remotely. I'm Aline. And before I actually start, I just wanted to publicly thank the organizers for the opportunity to be here, in particular to give this talk today. I'm very happy to be here. And yeah, so as the title of my talk suggests, today I'm going to tell you something about a specific GIT problem. So this is joint work with Masafumi, and I would like to report on our results. So in this project, what we studied is the GIT stability for linear systems of hypersurfaces of some fixed degree inside some projective space, and we obtained a complete stability criterion for this problem. So I would like to address that today. And my plan for the talk, or something that I hope to achieve today, is to try to convince you that this is an interesting problem, and I will do that by focusing on some geometric examples that I find interesting. Okay, so what is the setup? I'm gonna introduce some notations first, and then I'll move to the example. All right, so first let's fix a triplet of natural numbers, so K, D, and N. So these three numbers, they are going to play a role. They are going to appear throughout the talk. Let's let V be the following vector space, so the space of sections of O1 and Pn, and G for us is going to be then S of V. And now let's consider X, K, X and K, D, N, so the same numbers here, to be the space of all k-dimensional linear systems of hypersurfaces of degree D in Pn. So K is the dimension of the linear system, D is the fixed degree of the hypersurfaces in that linear system, and N is the dimension of the fixed projective space that I'm considering. Okay, so what is the guide there? So L in X KDN, I'm going to think of these and use this notation. So a linear combination like this. So the HIs are just given as the zero locus of some homogeneous polynomial Fi, and then I think as the lambda i's as the coordinates in a pk. So lambda 1 through lambda k plus 1, this is the point in And now, before I move on, maybe it's worth mentioning that depending on where you're coming from, there are different points of view for such an object. For example, maybe remark, so in L, like this in X KDN, you can view it as a divisor of by degree 1 comma d in a product of projective spaces, so pk cross n, or if the base locus of the linear system has the expected dimension, meaning the base locus is a complete intersection, then maybe you're interested just in the base locus. So if L is what we call regular, then base locus is a complete intersection. Or yet, maybe you're interested in the rational maps associated to these guys. So just for you to have in mind, maybe you want to consider this from different points of view. All right, but in any case, so what are we doing? So if we pick an L in X KDN, what we are doing is that we are picking a K-plane inside the space of all hypersurfaces of degree D. Yeah? So in particular, what I'm going to do is that I'm going to identify X with a Grassmannian. So the Grassmannian of K-planes in S dV, so the diff symmetric power of my vector space V. In particular, I'm going to view this variety sitting inside some large projective space via the Plucker embedding.
What is this K plus 1?
I mean, I'm saying that this is the notation that I'm using. Yes. I have K plus 1 things here. And yeah. Now, so what is the GIT problem that we want to consider? So this is the group G, FLV. There's a natural linear action on V. And that's going to give us a natural action on this Grassmannian sitting inside the projective space. And this is exactly the GIT problem that we want to consider. So our so G is acting here, and our goal, let me put this in quotation marks, is to describe the quotient. And I'm putting in quotation marks because so the goal of our project and what I'm going to address today is really just the first step in the description. We want to describe what the stable and semi-stable points are in the sense of GIT. Okay, so this is the general problem that we are interested in, and towards the end of my talk, I will tell you what is the criterion that we obtain. But now I want to sort of focus on particular instances of this problem that, as I said in the beginning, have some interesting geometry. So I'm not a very tall person, so if you cannot see on this board, please let me know. Okay. Let's call this paragraph 1 motivational examples. And example 1 is the following. So I would like to take a look at a very classical construction, which is the following. So I'm going to start with 2 cubics in the plane. So say C1 and C2. And I'm going to look at the pencil defined by them. So say lambda 1 C1 plus lambda 2 C2. Yeah. So this defines a rational map from P2 to P1, which is given by evaluation. And this is only rational because it's not defined precisely at the 9 points where the 2 cubics intersect. Yep. And if we want to resolve this, what do? We just blow up the plane at the 9 points. So let's consider the blow up of P2 at the 9 base points of the pencil. And what do we get? So we're going to get a rational surface, yeah, that comes equipped with the structure of a genus 1 fibration, meaning it has some proper surjective morphism to a curve, in this case P1, with connected fibers, such that the generic one, it's a smooth curve of genus 1. So the generic fiber, sorry, smooth curve of genus 1. And in fact, the morphism here comes from the anticanonical class of the surface, so let's call this surface X. So such surfaces are called rational elliptic surfaces, and they have this, this property. That so there is a horizontal curve that intersects each fiber once, and you can take that to be the exceptional curve over the last blow up, over the last point that you blow up. Okay. So this is a section. This gives you a section for the vibration. So you start with a pencil of cubics in the plane. You obtain a rational elliptic surface with a section, and in fact, you can show that surfaces with such a structure have to come from a pencil of cubics in the plane. So this is very classical construction that was considered by Miranda in this context of GIT for linear systems. So Miranda in the 80s, in his very first paper, he described the GIT stability for pencils of cubics. So and the criterion that he obtained was in terms of some kind of geometric data coming from the elliptic surfaces. So in terms of the geometry, let's say, of rational elliptic surfaces. So RES stands for rational elliptic surfaces. In fact, so the criterion is in terms of the types of singular fibers appearing on the surface. So I know this is very vague, but the result is very concrete.
Is the answer simple?
Sorry?
Is this answer simple?
Yes, if you'd like, I can write it down. Yeah. So first, maybe I can say it in words. Yeah. So first, he shows that a pencil of cubics is going to be GIT stable if and only if, first of all, it contains a smooth member. In particular, it's going to define a rational elliptic surface, and then all the fibers appearing there are non-reduced. Sorry, yeah. The moment I said yes. And then for semi-stability, so if you restrict to the pencils that contain a smooth member, what happens is that you allow one extra type of singular fibers, which in Fédérale's notation are the IN stars. So it's very concrete, perhaps you can say simple. Okay. So this is the first example to serve as a motivation, and it's also how I got interested in this. Now, I want to move on to the next example, but the next example starts from this picture, actually. So we have this classical correspondence, right? So we have curves of degree 3, and we construct these surfaces with an elliptic vibration. Now, it turns out that this picture somehow generalizes in the following way. So now, what I will do is to consider certain pencils of curves of degree 3m, which are called usually Hoffen pencils. And I apologize for my pronunciation. I was a French mathematician, so I'm pretty sure that's not how you say it. Anyhow, so here's what we do. So take C, a smooth cubic, and consider the usual group law on the cubic. And let's pick 9 points in the cubic, so P1 through P9, such that their sum is an M torsion point. So M times P1 plus P9 is 0. And this M is minimal. Then there exists a curve of degree 3m that passes through these 9 points. And it has geometric genus 1. So in particular, this curve will have singularities at the point. It's going to have a point, an ordinary multiple point at each pi of multiplicity m. That's why you get this genus 1. So singular at the pi's. And then, okay, so if you consider, we have this curve. So now let's consider the following pencil. So I'm going to look at lambda 1 C 3m plus lambda 2. I'm going to take the cubic that I started with multiplicity m. So I get some type of pencil of curves of degree 3m, and I claim that out of this pencil, so if we blow up the 9 base points, I'm going to get a rational surface that carries again a structure of genus 1 fibration. So blowing up the PIs, we get, say, surface Y. Let me just call Y. And now the fibration is given by minus m, the canonical. So the difference here is that if m is bigger than 1, then the surface, the kind of surface that we will get will no longer admit a section. In fact, we will always have exactly one multiple fiber of multiplicity m that comes from this multiple cubic. Nonetheless, it still makes sense to ask the question, can we try to relate the GIT stability for these pencils to some kind of geometry attached to these surfaces Y that we get? Yeah? So GIT, let me put this as a question. So what about an analog of Miranda's result? So this problem is something that I started considering during my PhD. So the case m equals 2 is the case that I consider. And I obtained some explicit statement similar to this, a bit more complicated. And then in this joint work with Masafumi, we treated the case for of all possible m's. So let me state this as a theorem. So we proved the following. So let P be one of these pencils so we call them half a pencil of index m. The m is the same m appearing here. And I'm thinking of these as a point in x1, 3m2. So if P is unstable, respectively not stable, maybe I should write the other way around, then on the surface Y that I get, there exists a fiber F such that the law canonical threshold of y comma f is less than 1 over 2m in the unstable case and less or equal on the non-stable case. So we get some condition in terms of the of this invariant of singularities, but since you know, we know what are the possibilities for f. So in the end, this is very explicit, and we can compute it quite easily. And perhaps what's interesting to mention at this point is a direct corollary of that.
Is the converse true?
I'm gonna get there, yes. Okay. I'm gonna get to the question in just a minute. Okay, so what is the corollary? So if m is bigger than 3, then all such p's are stable. If m is 3, then all such p's are semi-stable, and stable if we do not have a 2-star fiber. So for m bigger than 3, the converse is trivially true. And for m equals 3, it is true except for one example. Sorry, just give me a minute because I'm going to write down the example. So the converse of theorem is true except for a few examples. So let's put it like this. So when m equals 3, there is just one family that gives you a counterexample. And then when m equals 2, there are more families. And it's a bit more complicated, so I'm not going to go there.
Do you know which of the semi-stable things are polystable?
We haven't looked at that yet. Yeah. But I think maybe one idea, sort of mimicking what Miranda did, would be to look at the J invariant, and I think yes.
So this is more like a speculation.
Yes.
If you have one hypersurface, then LCT lower bound implies GIT stability.
Yes.
The converse may not be true, but you can remedy this by wall crossing of K moduli.
Mm-hmm.
So I wonder if for linear systems, whether you have a wall crossing.
I think you know, you started your question by providing some evidence to why maybe this is true, right? And because of that, I think it's possible. So I'm going to present later like what is the GIT criterion that we obtained, and somehow we go back to the hypersurface case. So I think it's worth investigating. I was saying, okay, so the converse is true, except for some examples, and I'm going to give the example. Okay, so consider C to be the following cubic. So here alpha and beta are some parameters, but they cannot be 0. Q is going to be this conic, and then L is going to be this line, and then the pencil that you take is the following. So you take the conic with multiplicity 4 plus the line, and then you take the cubic with multiplicity 3. So this has just 2 base points. You have to blow up one of them 7 times and then the other twice. So you are going to get a surface that has a fiber of type 2 star, but the pencil is stable. So this is GIT stable. Okay, so this is the sort of unique family of counterexamples to the converse of the theorem when m equals 3. Okay. So now let me move on to the next example, and then finally I will state the criterion. Example 3. Now I'm going to look at k dn equals 2, 2, 2. So I'm going to look at nets of conics in the plane. So again, this is very classical, and it has been considered before. So Wall has a description, maybe 84. So he has a description of GIT stability in terms of the discriminant curve of the net. So let me call it that delta. So this has degree 3. So it's actually 83. Okay, so what he proves is that n is stable if and only if delta is smooth, and n, I mean a net of conics is stable if and only if the discriminant curve is smooth, and n is semi-stable if and only if this cubic has adverse nodes. So again, it's a very explicit description. Yes.
Stability for GM3.
Yes.
Okay, as you mentioned, it's divided into 1, 2, 3, 2 cos P2.
Yes.
The natural action of 2, 3 times.
Yes.
Will it be the same?
Wall has a result that, as far as I understand, tells you is the same.
It's the same.
Yes.
It's what Fédérale told me, but no problem.
Yes. Yeah. And in fact, that was going to be like my next observation. Yeah. Exactly. So maybe one reason why looking at this particular instance of the problem is interesting is the following. So n in x222, you can think of this as x, maybe y, a divisor of by degree 1, 2 in P2 cross P2. And in fact, this is funnel threefold in family 2.24, I think. Yeah. So, and as far as I understand, if you look at the GIT from on the right-hand side, it's the same as GIT for on the left-hand side. In particular, I can now mention the word K-stability at least once in this talk. So I'm going to state this as the following proposition. So if y is smooth, then y is GIT semi-stable. It's more than that, but and it's going to be strictly semi-stable if the net, the corresponding net, contains a double line. In particular, then you can show that X is strictly K semi-stable if N contains a double line and it has no base points. Right. So an extra maybe motivation in the context of this workshop for looking at this particular problem. So let me now finally.
Usually, K-stability implies GIT is easier. Reverse
Yes.
implication is hard. So
Yes.
how do you prove who prove?
So you have to use. Maybe Masafumi can help me with the names of the people. I'm not very good at this. So you put this inside a family.
The family consists of the pure one. Anyway, we can discuss that. Okay.
So you put this inside a family over P1, such that the central fiber is K polystable, and then it's a general phenomenon that allows you to conclude that.
What was the question?
It's the same argument that they use in the Fano book about the Calabi problem. It's the same.
Yeah, that's what I'm.
Yeah. Yeah. So here I just wanted to mention it, how it connects with what I'm talking. Okay. finally, so this is a possible approach to the general problem that I started with. So now I would like to really tell you what the stability criterion is that we obtain. So theorem is the following. So what we observe is that. Yes?
It's compass.
Say it again.
It's compass. I think.
What?
First case instability implies that contains some. I mean yeah.
The implication.
The implication is
implication there is of.
Yeah, so I mean the third case instability implies console. I mean.
That's you can. What you can.
Double line means what? It's discriminant curve has not.
Mm-hmm.
Two.
Mm-hmm. I'm confident that the conclusion is correct. So X is going to be strictly case semi-stable if this happens.
No.
Yes.
The case is stable. Implies.
In terms of discriminant curves, it's strictly semi-stable if it's singular but not stable.
So like
Exactly. Yeah.
this is one-dimensional K-model.
Yeah.
So you guys did it.
Yeah. So I would say if it's but it's smooth, this condition is smooth. So it's coincide with the GIT for cubic curve. So if it's singular but not three lines, then it's strictly case.
Yeah. Okay, so what is the theorem that we proved? So if I pick a point in x kdn, this is not stable, respectively unstable, if and only if there exists a choice of generators h1 through hk plus 1 such that their union defines a hypersurface which is itself not stable or unstable. Okay, so what's crucial here is that we remind ourselves that the action that we are considering really comes from the action on V. In particular, there's also an action on the space of hypersurfaces of degree k plus 1 times d. And then we relate, we consider the GIT problem over there, and then we, for the generators of our linear system, and we obtain this criteria. So let me now just finish by going back to the examples that I consider and see how we can actually apply this result. So what happens is that in the first and the third examples, so the triplet of natural numbers that we considered were the following. So first we considered pencils of cubics, so 1, 3, 2. And then we considered nats of cubics, so 2, 2, 2. And then what happens is that 3 plus 3 is 6, and 2 plus 2 plus 2 is also 6. So if we now look at what this is saying, it says that we can derive something about the stability for pencils of cubics in terms of plane statistics, and the same thing for the nets of conics. And the point is that Shah in the 80s also considered this GIT for plane statistics. He was looking at constructing a moduli for K3 of degree 2, and in particular he described this GIT picture. So if we combined the criterion that he obtained with our theorem, then we can recover both Miranda's result and Wall's result. So let me just, for completeness, write down what his criterion is for stability. So a plane static is stable if and only if it has no multiple lines, no consecutive triple points, and no points with multiplicity greater or equal than 4. So for example, if you go back to the case of pencils of cubics, so you look at any two generators. So we're talking about cubics, right? So when I look at the union of the two cubics, that's a static, and it cannot contain a multiple line in order to be stable. So the cubic itself cannot contain a multiple line. And then in here, the fact that the consecutive triple points and points with multiplicity greater or equal than 4 cannot appear, it essentially tells you that the pencil has to have a smooth member. And then you put these things together and you figure out what are the types of singular fibers that appear in the corresponding rational elliptic surface. And then, again, we have very explicit geometric description for the semi-stable case, and you play the same game. So this gives one direction. For the other, you need to know how to construct the rational elliptic surfaces from pencils, which is not so bad. And for nets of conics, we can play the same game. It's just a bit more involved. And the point is that you need to know what the dictionary is between a net of conics and the discriminant curve, which is to say you have a plane cubic and you need to figure out how to write it as the determinant of some symmetric 3x3 matrix. Once you figure out that, then it's a sort of straightforward to apply Shah's results combined with our theorem. And I think I would like to stop here. So thank you so much for your attention, and please do ask questions.
Does anybody have any questions?
Did you try examples?
We are about to. Yeah, yeah. Personally, I'm interested in linear systems of quadrics in general, just because there's a lot going on. Yeah, yeah.
Principal quadrics is better.
Yes. Yeah, yeah, yeah. No. I mean, in some cases, yes, but it still would be nice to see how, if this provides something new or it simplifies some argument or not. Yeah.
So do you see the log canonical thresholds coming in because you know the values of the log canonical threshold, or does it come in naturally?
Yeah. So the point is that we have this. This is something that Yushan, that's your name, right? I think, yes. So he mentioned at some point today about, you know, if you know that you have some bound on the log canonical threshold, then you can conclude something about stability. So you have that for hypersurfaces. And then the point is that if you are looking at a vibration, like we were, okay, so there is some kind of vibration in the picture, then you can compare the log canonical threshold for the, you know, the pair P2 chromosome curve that is coming from the pencil with the log canonical threshold of the pair on the surface. And because you know that there is this relationship for hypersurfaces, then you could expect it to figure out something for the vibration. So that's how where the idea came from, and yeah. And but to sort of complement my answer, I mean you also know that there is a finite and small list of singular fibers. And it's easy to compute what the log canonical threshold is. For example, if you try to do the same thing for pencils of, for vibrations on surfaces, but now the genus is no longer 1, then as far as I know, there is only a complete classification for genus 2. But then there, the list is huge. It would still be possible, but it becomes...
Any more questions? If not, let's thank the speaker again.